Welcome back. System of particles and rotational motion extends mechanics beyond simple point objects, covering how extended, rigid bodies rotate, and introducing the rotational equivalents of the linear concepts you already know. In this video we'll cover center of mass, torque and moment of inertia, and angular momentum conservation. Let's begin. The center of mass of a system of particles or of an extended rigid body is a specific mathematical point that represents the average position of all the system's mass, weighted appropriately by each individual particle's own mass, and remarkably, the entire system's overall translational motion can be fully and accurately described by treating the whole system as if all of its total mass were genuinely concentrated at this single point, with the total external force applied there. For a symmetric, uniformly dense object, like a sphere or cube, the center of mass simply coincides with the object's geometric center, but for an irregularly shaped or non-uniformly dense object, it can actually lie anywhere, including, in some specific cases, entirely outside the object's own physical boundary, like a ring or hollow donut shape. A particularly important elegant property is that when no net external force acts on a system, the system's center of mass moves with genuinely constant velocity, or remains completely stationary, regardless of how complex, chaotic, or violent the internal motions and interactions between the system's individual constituent particles might be. This is precisely why an exploding firework's overall center of mass continues along the exact same smooth parabolic trajectory the original, unexploded shell would have followed, even as the individual fragments themselves scatter unpredictably in every direction. Torque is the rotational equivalent of force. It's what actually causes an object to begin rotating, or to change its existing rotational motion, and it's calculated as the product of the applied force and the perpendicular distance from the rotation axis to the force's specific line or action. This perpendicular distance is called the moment arm or lever arm. Torque genuinely depends not just on how much force is applied, but critically on exactly where that force is applied and in what specific direction. This is precisely why a door handle is deliberately positioned far from the hinge. Applying the same push force far from the hinge produces significantly more torque, and therefore opens the door far more easily than applying that exact same force very close to the hinge itself, where the moment arm is small. For rotational equilibrium, an object at genuine rest, or rotating at a steady unchanging angular velocity, the net torque acting on it must equal exactly zero. This specific condition, alongside the standard condition of zero net force for translational equilibrium, is essential for correctly analyzing balanced, stable, stationary mechanical systems, like a seesaw resting in perfect balance. Moment of inertia is the rotational equivalent of mass. It's a genuine measure of an object's resistance to any change in its rotational motion, exactly analogous to how ordinary mass measures resistance to changes in linear translational motion. Critically, unlike ordinary mass, moment of inertia depends not just on how much mass an object has, but also very significantly on precisely how that mass is spatially distributed relative to the specific rotation axis being considered. Mass located farther from the rotation axis contributes disproportionately more to the total moment of inertia than an identical amount of mass located closer to that same axis, since moment of inertia scales with the square of the distance from the axis. This specific distance squared dependence directly explains why a solid disk and a hollow ring, sharing exactly the same total mass and identical outer radius, have measurably different moments of inertia. The ring, with all of its mass concentrated at the maximum possible distance from the central axis, has a distinctly larger moment of inertia than the disk, which instead has mass distributed at every distance from 0 up to that same maximum radius. This is exactly why a solid disk or ball reliably rolls down an inclined ramp faster than a hollow ring or hoop of the identical mass and radius. The ring's larger moment of inertia means more, or the available gravitational potential energy must convert into rotational kinetic energy, leaving comparatively less energy available for translational forward motion down the ramp. Angular momentum is the rotational equivalent, or linear momentum, calculated as the product of an object's moment of inertia and its angular velocity, and the law of conservation of angular momentum states that when no net external torque acts on a system, its total angular momentum remains genuinely constant over time. Since angular momentum equals moment of inertia multiplied by angular velocity, if a rotating system's moment of inertia changes, its angular velocity must correspondingly change in the exact opposite direction, to keep their product, the total angular momentum, genuinely constant throughout. Decreasing moment of inertia must be exactly compensated for by increasing angular velocity, and vice versa. This precise, elegant relationship is beautifully and directly demonstrated by a spinning ice skater. When the skater deliberately pulls their extended arms and legs in close toward their body's central rotation axis, they significantly decrease their own moment of inertia, since their mass is now distributed much closer to the axis, and consequently, to conserve angular momentum, their angular velocity dramatically increases, causing them to spin noticeably faster, and conversely, extending their arms back outward again increases moment of inertia and correspondingly slows their spin rate back down. Let's recap. The center or mass represents a system's average mass position, moving at constant velocity, when no net external force acts, regardless of internal complexity. Torque, force times moment arm, is the rotational equivalent of force requiring zero net torque for rotational equilibrium. Moment of inertia, the rotational equivalent or mass, depends critically on how mass is distributed relative to the rotation axis, scaling with distance squared, and angular momentum, moment of inertia times angular velocity, is conserved without external torque, beautifully demonstrated by a spinning skater's changing spin rate as they pull in or extend their arms. That's system of particles and rotational motion. Keep the angular momentum conservation relationship sharp. The ice skater example captures its essence perfectly for exam recall. See you in the next video.